So with molecules, the big skill that we learn, so this is nonmetals with nonmetals, the big skill we learn is how to draw those structures. So Lewis structures, and then the geometry and the shapes, and how those contribute to the polarity of the molecule. So once we have the polarity of the molecule, we can make predictions about its behavior. When we're talking about ionic compounds, so a metal with a nonmetal far apart, right, far apart on the periodic table, then our big skill is naming. The naming is more challenging because we have to use the formula to find the charge and then name it appropriately, or we need to use the name to write the formula and know the relationship between the metal and the nonmetal. So it's just a different skill, right? These different types of molecules have different challenges in this skill that we're talking about. So that's where we're at. This is chapter 6, part 1, and that's just the naming component. So we'll go ahead and pick up where we left off. Okay, we left off on page 8. And I had asked you to work ahead a little bit if you can. So we are going to use the name of the compound to find its formula. So I mean the relationship between them. Now we started with calcium nitride. We know the charges on calcium and nitride, and so we're going to use the crossover method to form a neutral compound. So it has to be a neutral compound, total charge is 0. For calcium nitride, that would be Ca3N2. So there's 3 calcium ions for every 2 nitride ions. And we know that just by the name, just by the location on the periodic table. Okay, so we have some exceptions. These were some exceptions to the variable charges. Right, the rest of this stuff here under the staircase, these are variable. So we need a Roman numeral for those. Barium chloride, that will need 2 chloride ions for every 1 barium. Right, remember sulfate? Sulfate is SO4 2-. We need the smallest neutral subunit. So that's going to require 2 sulfates for every 1 lead. Now this is a neutral compound, so I am not showing any charges on the formula. The formula doesn't show any charges. Write your ions separately. Don't write them in the compound. Aluminum is a 3+ every time. It's group 3. Oxide is a 2-, so we'll use the crossover method to form a neutral compound.
Professor, did you mean to write the subscript 2 on the sulfate?
Yes.
You said it, but then you didn't write it.
Thank you. I appreciate it. Right. The charge on the metal is given, so this is an Fe3+. But we wouldn't know that. Here's iron, number 26, right? Yeah, number 26. So here's iron right here. We wouldn't know the charge on that unless it was given. So it's given. This is an iron 3. And it's paired with hydroxide, one of our polyatomic ions. So our neutral compound will. Again, hopefully you wrote your own chart that's color-coded, but you can find them right here on the periodic table. So if you have your blank periodic table that I've asked you to print, that will be where you can look up those ions. The chlorate is ClO3-. So this is our fresh new one with all of the elements and their official symbols now that that's been decided. So that's ionic naming, metals with nonmetals. If it's a metal with a nonmetal, or polyatomic ions in the formula, or a name that ends in "ate" or "ide, those are going to be ionic compounds, and they follow the naming rules we've been working with here. If we're talking about molecules, molecules are covalently bonded with nonmetal, and for those ones we don't know the relationship. So let me give you some examples. Maybe you've had your car exhaust done, gone to the emissions testing. They're closing those all down now. Apparently the air is clean enough. You might see NOx, nitrogen oxides. These are components that lead to smog or acid rain or both. Nitrogen, on the periodic table, it's in group 5, so it goes -3, or it could go +5, or for any of those, it could go plus or -2. It does a bunch of different oxidation states. So we could have NO, we can have NO2, we can have N2O, which is laughing gas, nitrous oxide. We can have N2O2, we could have N2O4, etc. So that nitrogen can hold a bunch of different oxidation states, and we don't know for sure what charge it's going to hold based on the location on the periodic table. And that's why for molecular naming, we introduce these Greek prefixes, all this mono-di-tri business. We need to know what is the ratio. What is the ratio of atoms in this compound? And C bar is my little compound notation. So now we're going to name molecules, name molecular compounds. We have this need to give the ratio that we didn't have when they're ions. With ionic compounds, we know the charges, and that tells us the ratio. But for molecules, these have a clear boundary around them, and they could take a lot of different forms, as you can see from my example with the NO and NO2 stuff. So we need to give those ratios, and we're going to do it by naming the first element as if it was the metal. So it's going to get the element name. But of course, now it's a nonmetal, so that'll be something like nitrogen or sulfur. Okay, so it's going to get the element name. And the second element is going to get named as if it was the anion. And so it's going to end with IDE. Now, to give the relationship between them, we're going to give our Greek prefixes. So 1 is mono, 2 is di, 3 is tri. Now 4 is one of the challenging ones. 4, people want to write quad, but that's not the right one. It's tetra, like a tetrahedron, like our tetrahedral shape. So that one tends to be a little bit tricky. It's just one that we don't associate. We don't use it as much. Penta is pretty easy. 5, like a pentagon. 6 is like a hexagon. 7 is another one that's tricky because we want to say septa, but it's hepta. Octa, like an octopus, 8 legs. Nona is 9, and deca is 10, and that's all we're going to need. So it's really the 4 and the 7 that get a little tricky. Now, here's the other thing about naming molecules. If we were in the lab, I might show you a Merck index. Oh, I don't even know. I think mine's in my office at work. But they have these big, thick books that list chemicals, and they have paper-thin pages. Maybe you've seen them in the lab. And you look up this tiny print with multiple columns of chemical names. So those are listed alphabetically. And when you're looking at all of the compounds that could be made, if we put mono in the front, that M section would be impossibly long. So for that reason, if there's just one atom at the beginning, we don't put the mono. We just assume there's one. So you see that with carbon dioxide right here. In this formula, in this section, saying the first one with its Greek prefix, if there's just one of them, we don't use that Greek prefix. So that's easy to remember because a lot of us know about carbon dioxide, something we've heard about before taking chemistry, and it's not monocarbon dioxide. It's just carbon dioxide. So we would look in the C's on that section. So let's get to work. That first one has a sulfur, so we're going to name it with the element name and no mono, so it's just sulfur. 6 is hexafluoride. Now this next one has 2 chlorines, so we do use the prefix on that one. This is going to be dichlorine. And here we have an oxide with a hepta. A lot of times if you have that AO combination, We'll drop one of the letters. So I would typically write this as heptoxide. Now we have this group CPAC that standardizes our naming and they make decisions as a committee and they change stuff up sometimes. I think they're accepting both. So you could write heptaoxide as well and it's not technically wrong anymore. Either way is fine for me. If I grade that in the computer, I have to put in one answer. So it might mark it wrong and then I'd have to grade it right. This one is phosphorus. So we use that metal name, the element name, sorry. That's a non-metal, but it's named as if it's carrying the positive charge. But this is covalently bonded, so these are shared electrons. At best, this is polar covalent. All right, and then we've got 3 chlorine, so this is trichloride. So we end it with the IDE. Okay, and the last one, dinitrogen pentasulfide. That's it, naming molecules. We have to recognize which system to use. Is it a covalently bonded molecule or is it an ionic compound? And then use the system that matches that type of molecule. You need to know a couple common names: ammonia, methane, and water. These, oh yes.
When we say chloro, I wrote dichloroheptoxide. I was right.
You would use that in organic chemistry.
Only in organic?
Yeah.
Okay. Thank you.
Yeah, sure. That's a great question. I've never had that question before, so that's cool. All right. Now, these molecules should look familiar. We have drawn these molecules, right? These are all of the molecules that have a central atom with 4 groups around it. Steric number equals 4. For ammonia, it had 3 bonds and 1 lone pair. Carbon had 4 bonds, and water had 2 bonds and 2 lone pairs, right? So I'm just trying to tie in what you know about these molecules, and now we're giving them names. So you need to know ammonia. That will actually help with the polyatomic ions, because what if we took our ammonia and we combined it with a hydrogen ion? What's the charge on a hydrogen ion? Hydrogen is named as the element name, so it's positive, H+. It's in group 1. Put those together, and now we have NH4+. What's that called? Ammonium. As if it was a metal. It's not a metal, but it is an ionic. It's positively charged like a metal. So this is ammonium. And I see people, they want to make this an element, and I think there's americanium or something, AM. No, oh yeah, it is. It's number 95. So it's not that one. It's not an element. This is a polyatomic ion, but its name sounds like an element name because it's a positive ion. It's our only positive polyatomic ion. Okay, so blah, blah, just a bunch of extra information to help build the memory, right? Because you get to know these. It's like knowing 100 of your best friends. So ammonia. Methane is our standard tetrahedral molecule shape. It is the smallest hydrocarbon. So we usually use hydrocarbons for fuels. And it's completely nonpolar. And water, everybody knows water. Water is so important. So you have to know the formula for water. Now we're going to jump back a little bit and talk about the polyatomic ions a little bit more and bring them together with acids. So acids are substances that release H+ in water. It's just a chemical property. This was observed. And we notice that they taste sour, and we notice that they turn vegetable dyes different colors. So we're going to look at that in our acid-base lab, which is a fun lab. It's going to be cool. So that's what an acid does. It releases that H+. Acids are always aqueous. Even if they come as a gas or a solid, they grab water from the air. They like try to dilute themselves. So they're always, all acids are aqueous. When a strong acid, this one is a strong acid. And when I use it that way, the word strong is a technical term. And so HCl is a strong acid. That means it releases all of its H+. So that gives us a one-way arrow. HCl aqueous goes immediately to H+ plus Cl minus. So 100% towards products. So what that means is there's no molecules of neutral HCl. It's 100% ionized. And we can see that here both in the letters and in the drawings here where that hydrogen has attached to a water molecule, right? So what we're seeing down here is that H+ plus water is H3O+. Now water is never aqueous because it's pure substance. But essentially the H+ and the H3O+ are the same. They look the same. We write them in a similar way. It's just an issue of balancing and showing the water molecule or not showing the water molecule, just remembering that it's there. So for acids, we have a convention where we start the formula with the H. So these are our usual acids. These are some really common ones. That H in front can come off, and that's what makes it the acid, releases that H+. So a binary acid is just two things. Those all come from, like, notice these guys are the halogens. They're the nonmetal side. H2S is also an acid. And then we get to the ternary oxyacids. That just means that there are three elements, and one of them is oxygen. That's not really the important part, though. The important part are these ions here. Do you recognize your polyatomic ions? So these polyatomic ions are so stable, they function as a unit. They're so stable that they are happy to give up their H+. They don't need them because they're so stable in solution, sharing all that charge together. So the polyatomic ions are stable and easily released plus. So I wanted to make that connection between the polyatomic ions and their stability, the fact that they exist as a unit, that we're working with them like that, together with the idea that if they're paired with hydrogen, they just let that hydrogen go, and that gives us acidic properties. We have a couple different kinds. We can talk about monoprotic. These ones give up just one hydrogen. We also have polyprotic, so we have diprotic acids, and we have a triprotic acid. So we take that ionic charge and we pair it up with enough hydrogens to make a neutral compound. And that's how we can connect the idea of our acids with those polyatomic ions that we were working with. Okay, so let's name them. We're going to go ahead and do naming here. It's not my favorite order. I like to kind of learn about stuff and name it at the same time. But a lot of textbooks have you memorize naming and then later you learn why we have different systems of naming. So we're going to go ahead and do acid naming now. But I don't usually put that on exams or quizzes for at least a little while. So if it ends, in general, if it ends in an IDE, and it's just two things, so it's a binary acid, then we're going to add hydro, and the IDE turns into the ic. So fluoride ion, if we make a neutral compound with hydrogen, that will give us hydrofluoric acid. If you have an ion that ends in ITE, then we're going to keep the name the same. We're going to drop that ITE and it's going to become us, nitrous acid. So we put an H on it to make a neutral compound. That makes it an acid. And it's named nitrous acid if it comes from an ite, so like nitrite or sulfite. If it's an ATE, then that's going to turn to an ic. So nitrate ion paired with an acid, with an H plus to make an acid, becomes nitric acid. Okay, so let's do some of these. The exception is phosphorus, because we dropped the OR to make phosphate ion. So this is going to be named phosphoric acid. It's a little bit of an exception. Okay, so let's get some practice. We're going to write the name of our ions, and then we're going to write our formula for the acid that gets formed with hydrogen, and then we're going to name it. The first one just takes one H and all acids are aqueous, so I'm going to write that just to help remember. Two things, so we add hydrobromic acid. So this is a good way, this is a good time to use your color-coded chart that you wrote for your ions and refer back to it so you can learn to remember them. So we have the sulfate ion. So that 8 turns into an ic, sulfuric acid. All right, we've got hydrochloric acid. Maybe that's familiar. Hydrochloric acid is in your stomach contents. The next one might be tricky to remember. I like to write it in a different convention. So on the periodic table I've given you, I wrote it out like that. I'm not sure if I drew this structure, but I like to write it this way because it brings to mind the structure. This is pretty special. Does anybody know what we handle acetic acid in? Where might you have experienced that? I think everybody's eaten it.
Vinegar.
Hydrochloric acid is found in the stomach. Lemons contain citric acid, like a citrus fruit. Acetic acid is found in vinegar, but that's correct. Vinegar is acetic acid. So in our convention, we might write the H in front, and then we have our C2H3O2 aqueous. That follows the convention where one hydrogen is in front because it's acidic, and the other hydrogens are not together with it because those ones are not acidic. So I want to draw the structure for you. Maybe I'll draw that right over here. This looks like our structure. I'll draw it on the side. Those hydrogens on the carbon are not coming off. They're not acidic. Then we have our C double bond O, O, H. So that group right there, that COO, it looks a little funny. This hydrogen right here, that is the acidic hydrogen. It can come off because it's with those oxygens. They're like, hey, you can take, we've got each other. Those oxygens can share electrons with each other through resonance, and the hydrogen can just go. It can just take off. That's fine, right? So I like the structural, I like to write the CH3COOH because that group, that COOH group, is your usual organic acid. That is the same group in citric acid. Citric acid has 3 of those. And what other acids do we encounter? Tannic acid, all these acids that we see in our food and in life and biological molecules, they're usually a COOH. Again, I'm just trying to give you some detail and some connections to help remember the things that you we'll take out of the class. And remember, what's acetic acid? Oh, it's in vinegar. Has the same group that a lot of different organic acids have. And also, as a student, I found it very hard to remember that formula. I just couldn't do it. So I like to write it out like the structure. Maybe I'll leave that on the page for a second. Okay, SO3 is what? That is sulfite. So up here in purple we had sulfate, and down here we have sulfite. They're both the same charge, so they both need 2 hydrogens. But it's going to get a different name. Sulfurous acid. And I've told you you don't have to remember cyanide as a polyatomic ion. It's fine. I'll give that to you. Oh, you have it. Is it on here? Yes, it's on here. All right, that IDE. Now, I think by our naming system, we're going to call this hydrocyanic acid. I also see it as just cyanic acid. Sometimes they drop the hydro. So I still haven't figured out who said what when and which one's right or wrong. So either one would be okay. If you look it up on Google, you'll find both. They're both listed in the Wikipedia entry. All right, carbonate ion. This one is super important and it's so familiar. Does anybody know where you drink your carbonic acid? Oh, let me name it. Any carbonated beverage. All of your sodas, your bubbly water. Carbonic acid decomposes and gives you CO2. So as soon as you open it, the carbonic acid decomposes into bubbles. So all of our sodas have carbonic acid in them. Carbonic acid is also very important in the bloodstream, and also in ocean acidification. So very important and interesting acid all over the place. We are almost done with this section. Is there more? Oh, then we get into the numerical stuff. Okay, so perchlorate. Remember, this is the highest oxidation state, so it has the per and the 8. We're just going to keep those the same. So HClO4, aqueous. The 8 turns into an ick.
Professor,
Yes.
how do we know like how many hydrogen is on the acid? Like
From the charge.
Oh,
We have to make a neutral compound, and we're going to do that by adding the H plus to it. That's because acids release the H plus, so we know what we're adding when we make an acid. It's just a very special type of compound. Another way to think of it might be to think of, these are all nonmetals, right? These are nonmetals with nonmetals that act like ionic compounds. So they're their own special thing, acid-base reactions. Same thing down here, we had the low one is the ClO2, so we're going even lower. And that might be familiar or necessary in medical fields again, like sodium hypochlorite is a heart medication, right? So this would be hypochlorous acid. All acids are aqueous. Now, we're back into that system for this textbook where they just throw in some of the mathematical stuff right at the end. So we've got like 3 major topics in chapter 6. Naming, and then acids, and then now we're going to look at more calculations. So we did this in chapter 3 as well. In chapter 3 we talked about going from the number of molecules of an atom to the number of moles of an atom. Do you remember moles? So let's take a look at ethanol.
Mm-hmm.
This one is an alcohol.
Okay.
It's not acid or base. But when we get that COOH, And this could be any group on the end. In chemistry, we'll call it an R group.
R group. Okay.
Yeah, just any old carbon, hydrogen, whatever, something else. But this one is acidic. And that's because it's with these other oxygens. So this COOH is an acidic group.
Thank you.
And that's different from an alcohol. That's just a RCH2OH. That's our alcohol group versus our COOH. This is a carboxylic acid. And I always remember that because it looks like a box. So again, that's some extra information. I'm not going to ask you about alcohols at all, except maybe to draw one, right? Because we can figure out the shape and the structure. But I'm not going to ask you about any reactivity or even to name them. Okay, so next up we're going to get back into some mathematical stuff. So please review here. So we've seen molar mass before. Have a good day.